Okay, so thanks for being here today. Today is at AJS. The speaker of today is Michele Motta, that will talk us about a concise introduction to motion planning technically.
So, good afternoon to everybody. Thank you for coming here despite the strike of the buses. And thanks also to the organizer for inviting me to speak here today. So my talk today will be about motion planning. So the plan of the talk will be the following. First, I will describe what is motion planning in general and how it can be formalized with some mathematical tools. And then in the second part, I will show some example of what is more concretely motion planning. And then in the final part, I will talk about motion complexity, which is quite important topic in motion planning. So let's start. So in in engineering and especially in robotics, a problem that happens that one wants to solve very often is how to move something which usually can be a robot or a general machine to from some initial point to a specified target. And you want also to avoid obstacles and some other so staying maybe in a certain region or some obstruction on the motion. And but this is also more general and the same way you can formalize also the problem of moving a sofa from a room to another one. So the fact is that you want to move something from an initial state to some target. And so in this particular example of the slide, for instance, you can move speed up, then you go avoid this obstacle, and then cross the target. So from a mathematical point of view, this problem can be formalized as follows. So we have to find an appropriate set omega, which is the set of parameters that describes the state of our system. This omega usually is a subset of Rn or a subset of a manifold. And so once you have an initial and a final state and the prescribed time, what you want to do is find a feasible path that connects the starting point, the initial state, and the final state. So what does it mean more rigorously, this feasible path? So what is feasible? So we have basically two kind of restriction of on the path that we want to find. So first of all, we have the so-called state constraints. That is, we have a constraint on the set of parameters. So as I told before, this means that you cannot go everywhere, but you have to stay maybe in some region of the space, and you want to avoid obstacles and so on. And this is formalized saying that our path X must belong to the state space. So notice that in general, our state space may also depend on the time. For instance, if you have a robot moving in a crowd, then you want that the robot doesn't collide with people. So people moves, and so you have moving obstacles. And so this is the first class of constraints on the motion. And solving this first step is means that we want to determine whether the set of state space is path connected or not. So, but we have also another class of constraint on our path, which are dynamical constraints. Indeed, usually robots or other machines cannot move in direction or so. So they have constraint on the motion. So and these can be modelized very well using control theory. That is, in order to describe the dynamics of our system, we have a dynamical system where the right-hand side depends on the time, and we can choose this function, which is the control law. And okay, this is a function of the time. And depending on the problem, this function can be either L2 or infinity, or can have some other another prescribed regularity. So, so if for each choice of u in this set u, this f is a smooth vector field. Okay, so we have the system describing the dynamics of we have the dynamics, and so we want to find a path between initial state and final state, which is not just a connected path in our state space, but is also a solution of this control system. So summing up, we have a two-step problem. So determine first if our state space is connected, and then find a path which is admissible for our dynamics. So usually this second step is called controllability. If your system before is called controllable if for every starting and initial configuration you can find a path which is a solution of this dynamical system. We start from the initial point and ends in the final point. So we have so in order to solve a motion planning problem, we have to solve these two steps. And well, today we will focus more on the second step. So we will assume that our state space is always connected. Okay, so this was the general formulation of the problem. Is everything clear up now, or your questions? Okay. So let's see some examples. So the first class of control system, which one can use to model system of robots, for instance, is a linear system. So you have the state that is described by x, which is a vector of Rn, and the control is a vector of another Rn, which stays in a subset for u. And okay, and here A and B are two fixed matrices. So this is a very easy class to use. Then you can have also a control linear system. And here this is a little bit more complicated because you have nonlinearity with respect to the state space. And so you have the system is still linear with respect to the control. And okay, so here the velocity of your system is a linear combination of some admissible direction, which are along which you can move with your system. So, for instance, if here you choose every control equal to 0, then just the first one equal to U1. This corresponds to move along the flow line of the first vector field. And of course, you can mix up, choose the vector fields and so on. Another class of control system that one can use is a control affine system, which are very similar to the previous one. But now they are not anymore linear in the control, but they are affine. So you have some vector field that you cannot control. And this, for instance, describes some situation in which you have some external forces and you cannot control them. For instance, if you have a plane, you can control the plane, but if you have some wind, some external force, you cannot act on the wind. You have this wind, you have to manage it. So a more concrete example of control linear system is this one. So we have just our dimensional system. So the second derivative of y is equal to our scalar control. Okay, we can rewrite the system in this way, and we want to determine if this system is controllable or not. And okay, so using the notation that I introduced before, this is the matrix A, this is the matrix B. So to study controllability of a linear system, there is a very useful result, which is Kalman theorem, which says that if the span of a to the power j multiplied by the column of the matrix B, if these vectors span the whole Rn, these linear systems are controllable, so you can move from any point to any other final state. And in particular, in this particular example, you can see that a to the power 0 times b is simply b, and a b is the vector 1, 0, and so these two vectors are independent, and so they generate the whole R2, and hence the system is controllable. Okay, these models are very simple, so everything is linear, everything is well behaved. But they are very effective to describe the concrete situation. So, for instance, to control a pendulum, a vertical pendulum, you can make a picture to describe the situation. So the situation is the following: you have a pendulum which starts from here, and so this is so this is the base point of the pendulum, and this is vertically goes up, and so you have gravity that goes down. Here you have your point x, and you want to control this point in order to maintain the vertical configuration. And of course, here the dynamic is not linear. So there are very few examples in nature where the dynamics is linear, but nevertheless, if you use a linearized
Quanto è difficile trovare una password che non sia
Questo
debole.
questo?
Crea password con un token. Scarica.
So this is an example of this system is using a linear model to describe the dynamics of the pendulum. And you can see that even if you curve the equilibrium configuration, the system keeps the vertical position very well.
In this demonstration, we're going to see how we can rapidly design and validate a controller for a rotary input.
Okay. So let's go back to. Sorry, okay. Okay, that's it. So you can see that even if the model is very simple, it can be very, very effective. So, questo non si nasconde. Questo?
Yes.
Okay. So let's see now another example of control linear system in the design. So now we want to describe the motion of, let's say, a vehicle. So this is this model in literature is known as Dubinsky, but you can think, for instance, to the robot R2D2 from Star Wars. And so how does R2D2 move? So his state space is made by three variables. So the position on the plane, and then there is the orientation of the robot. So x1 and x2 are the position, and alpha is the orientation of the robot. And so here, for instance, you see that it's very natural to consider as a state space a manifold and not just simply Rn. Okay, so so this is the state space, and the equation of the dynamics the following. You want to represent the tangential velocity, so it's second and fourth. And then you have u2, that is the angular velocity. And so you see that if you want to go from any two position on the plane with a certain orientation, you can of course do this. So for instance, if you have points here, you are pointing in this direction and you want to go here in that direction, you just have to rotate rotate to reach this direction, you move like this, and then you rotate again to your favorite direction. And so this system is clearly controllable, despite the fact that you cannot move in any direction. So at each point you have just, let's say, a two-dimensional space of admissible direction. And in general, this is due to the fact that not only directions that are directly accessible, you can move also in a direction that are not directly accessible. And this is because if you combine the flow of two vector fields, you can approximate also the motion along the bracket. So if this bracket is not is linearly independent of the first two, you can move also in this new direction. And so you can iterate this process, and then you can reach all the brackets. And in this particular example, you can see that the bracket of x1 and x2 that are the vector fields in the example is this one, which is linearly independent of these two. And so you have all the you have that all the direction are accessible. And so this is more in general, this is known as a Chourashevsky theorem. And this says that if the algebra generated by the vector fields in your system, so these xk are, okay, these vector fields here. So if the Lie algebra generated by these vector fields is fully dimensional, so then you can move in any direction, and then your system is controllable. And so now comes a question. Are these two models, so control linear system and linear system, related somehow? They so we can study just one of them and then have information on the second one, or they are different. So the answer is that they are really different models, and this is can be formalized saying that if a control linear system is controllable, then it's never feedback equivalent to a linear system. And so feedback equivalence means that you cannot transform the one dynamical system in the second one, basically. So I put here briefly the definition, but it is not very precise. You can check on this reference. And so it is really important to study both systems, both classes of systems. So any question up to now, or everything is clear? So I go now to the final part of my talk, which is symptotic motion complexity of motion complexity. So first I introduce what is motion complexity. And okay, so new setting, we have a smooth manifold, which is the would be our state space. So describes the state of our system, and at each point of the manifold we have some direction which are admissible, and so we can move along these vector fields. And okay, these vector fields span a distribution on our manifold. So we can say that the distribution delta is the distribution of admissible directions. And okay, we can assume that we will assume that our vector fields satisfies the hypothesis of Chourashevsky's theorem, so that we can move, we can really move from any point to any other one. And so another consequence of Chourashevsky theorem is also that you cannot only move from any point to any other one, but also the metric induced by the length of the minimum length of this admissible path is indeed a distance on the metric on the manifold. And this distance induces also the topology of the manifold. So it's a good distance. Okay, so this is general setting. So now suppose that so we have our state manifold, and suppose that we have a curve that goes from a starting point and the final point. So we suppose that we can solve the first step of the motion planning problem. So we know that we can go from a point to another with following a certain curve, but this curve in general will not be admissible. And so if, for instance, this curve was avoiding some obstacles, we want to move close to this given curve. And so we using Riemannian distance. We didn't say it, the distance before was the Riemannian distance. So we can introduce the Riemannian tubular neighborhood of this curve, and we are interested in finding a solution of our control system that stays close to this curve. And so what we want to do is to measure how complex is this task. So how complex is to stay near to this curve. So just a brief recall, So an admissible curve must satisfy this equation. So the velocity of the curve must be a linear combination of the admissible curve fields. And in order to measure the complexity, we introduce a cost function. And one possible definition of complexity for the curve gamma is the following one. You define the motion complexity to be the inf of the all possible. You evaluate the cost function on the space of controls, taking into account that the control must correspond to an admissible path. So it goes from the starting point to the final one, solves this system of equation, and then stays also in the tubular neighborhood. So you want to minimize this function on this class of path. And you divide by epsilon, which represent epsilon is the same the tubular neighborhood, and this epsilon more or less correspond to the cost of an elementary piece of the path QU. So okay, this is the definition of motion complexity. Let's see an example. So this is an example on the Heisenberg group, which is the most simple example in Riemannian geometry. And okay, so the Heisenberg group is just R3. So we have this coordinate on R3, X, Y, and Z. And we take these two vector fields. You can see that these two vector fields are independent at each point. And then if you compute so these two vector fields span distribution, and if you compute the bracket of the next two vector field, you see that this goes in the vertical direction, which is linearly independent of the first two. So we have that when the condition is everywhere satisfied. And in this case, as a cost for a path, we can use the Riemannian length of this path. And so what we want to do is to find the complexity of the curve gamma, which is vertical, in the sense that is this curve, so moves along the Z direction. Which is not accessible, is tangent to the bracket of the vector fields that span the distribution. So we have this curve gamma, which is not admissible in general. We want to see how complex is to stay close to this curve. So we have that again, the motion complexity of this curve is given by this formula. And okay, so admissible curve must satisfy this equation, and moreover, okay, to define the length of the curve, we have to specify a Riemannian metric on the distribution, and we can do this simply imposing that x1 and x2 are orthonormal. And so the Riemannian length is simply the integral of the control. And you can see that if we parameterize the control, sorry, if we parameterize the curve, we obtain that also this reparameterization is admissible with some other scale control. And so in particular, we can suppose that the velocity of our curve is constant. And this is a very, very important simplification of the problem. So if we take the previous system and we write explicitly in using this time polar coordinate, the system is can be written like this. So you see it's a very simple system. In particular, you see that if you move radially, you can move radially using one control, and then if you want to go up and down, you have to use the other control, and you have to rotate simultaneously. So in particular, from the third equation, you can write the control in function of the variable z and r. And if you so we want to compute so we want to minimize this function here basically. So we can write. So if we pick any control, this is greater or equal than just the integral of the second component. We can use here the expression that we have derived before. And okay, so here you use that we are inside the tubular neighbor, so R is smaller than epsilon. And then here, so you end up here. But now you can notice that Z dot must be always positive because you want to go up, and if you go up and down, you're not minimizing the function because the curve that you obtain is longer. And so you can drop the absolute value, and then you end up with this integral, which does not depend anymore on the control. It's just an integral on one-dimensional integral. So you have that for any control, you have this lower bound on the motion complexity. So so I was saying that so for any control, we have this lower bound that does not depend on the specific control. And is this a chain of inequality, or is this lower bound strictly less than the motion complexity? So we have this inequality. We want to see that if we have also the reverse inequality, or if this is strictly less. And indeed, this is inequality. And to see this, you can pick this specific control. So first, so you start from this initial point. First, you move in the horizontal direction up to the cylinder. So this corresponds to take the control V1 equal to, let's say, 1 until for time epsilon. And then you move just along the tangent direction on the cylinder, which correspond to take maybe I go back to the system. So yeah, first you use just this control, so you move radially, and then you use this other control. So and then the first one you take it 0, and this corresponds to rotate along the cylinder in the tangent direction, and you can move with constant speed until you arrive to the top of the cylinder, and then you go back. Let's go to the okay, and then once you arrive here, you go back to the final point again. So you can see that the contribution of this first piece and this second piece is just 2 epsilon, because it's just the integral of epsilon times the integral of 1 times the time, which is epsilon. And then for the second part, you have only to integrate from epsilon to t, capital T minus epsilon. Here the derivative is constant, so you can take it out. And then you have the same passage as before, but now we have that all the inequalities that we had before are now. So we have that we have equality for the this inequality is inequality. So this was a particular example. More in general, you have this theorem, which was proved by Romano Menendez, Jean-Paul Gaultier, and Henri Perez. We say that on if you have a manifold and a rank 1 distribution on this manifold, together with Riemannian metric on this distribution, basically the same estimates hold, and so it's just a bit more complicated to say with this small t alpha, which is okay. So you have that your distribution can be described as the kernel of one form. So you pick the differential of this the differential of this one form, and then so you have two linear form on the distribution. One is the metric, and the other one is the differential of this one form. And since this is non-degenerate, you have that there is linear transformation along the first gamma that does this work, and then you can pick the maximum of the eigenvalues of this matrix, and this is this coefficient alpha. And so the motion complexity of curve gamma is number here. Okay, so how do we prove this in general? This theorem. So basically, you want to reduce the general case to the Heisenberg case. So to do this, first you introduce normal coordinates in the tubular neighborhood of the curve, and because we are interested only in what happens in this tubular neighborhood. So, so in principle, you rectify the curve. And then you can find also normal form for the vector fields that, for admissible vector fields. And these correspond more or less to diagonalize this matrix here. And then you end up with something that is not really the example that I showed you now, but is something very close. And so you can more or less make the same computation. So what was my original contribution with, in collaboration with Dario Prandi, was to try to extend this result also to control affine systems. Now, if you want to consider control affine system, instead of taking a admissible path that satisfy the equation without the drift, you have this drift. And the very important difference is that now you cannot reparameterize the admissible curves, because before you use that here you can rescale the control, but if you rescale the velocity, then you have to rescale also the drift, and so you have a completely new problem that is a different problem. So you cannot reparameterize admissible path anymore. And for instance, on the SMM group, the equation is the following. So you add the drift, the functional is the same, and you can decompose the tangent vector of the curve gamma into two visible direction which are tangent to the distribution, and the other direction which is so it is interesting, just the case when this coefficient is different from 0, because otherwise you can move horizontally. This is easier. And also the drift can be decomposed. And again, you want the drift to be vertical. Okay, so the expression for motion complexity is the same. And okay, in order to study this problem, you have to introduce this quantity, which is the integral of the vertical coefficient of the drift along the solution of the uncontrolled trajectory. So you pick, maybe I wrote it here. No. Okay, so the system is so the system of equation for an admissible bucket is this one. So forget the first two equations. You pick the solution of this equation. So simply you put all the control to 0, and you see where the drift drives you. And so you pick this particular solution, you integrate it along the component of the drift, and see where you arrive. So basically, you see where if the drift pushes you enough towards your endpoint, or if you have to push more. So the result that we obtain is this: if this quantity, so if the drift takes you exactly to your endpoint that you want, you have this formula for the motion complexity. Notice that here you have just 1 over epsilon, not 1 over epsilon squared as before. And instead, if you if the quantity we introduced before is less, so you make less. So if you have to go also forward to respect to what where you arrive without controlling the system, you have to push a bit your system, but let's say less than what you would do if there is a no drift. So these two are two constants that I will specify after what are precisely. So this is the same part that we had before. And so if the drift is not strong enough to take you to the endpoint, you have to push a bit, and if the drift is too strong, you have to slow down. And okay, so as before, you can more or less reproduce the same argument. So you introduce normal coordinates in the tubular neighborhood. You have normal forms for your vector fields. Your equation is can be reduced to this form. And now, if you try to do the same computation as before, you want to find the lower bound for the norm of the control. You can consider just the second component, and if you use the equation, you can write the second control in this way. So you notice here that now we have this also this part. So in general, we don't know if this numerator is still positive or not. And so this is the main difficulties. So we want to determine if this control must have a sign in order to be minimized or almost minimized. And the answer is yes, this control has a sign. And okay, we achieve this in the proof of this fact, I think, is not very satisfactory to me now, but maybe there is some other way to prove it. So first, we proved that the z dot must be positive, because if you don't go up, if you go up and down, then this does not seem very optimal. And then using this fact, there are some tricks to say that also the two must be either positive or negative. So in the end, you have that if you have this inequality, so if the drift is not strong enough, then this part here is positive. You have, in order to be nice, to must be positive, and so you can remove the absolute value, and you end up with this formula. If instead the drift is too strong, this quantity here is negative, so you reverse the signs, and you end up with this formula. And these two are the E's that we started was in the statement of the theorem. So this is all for what I wanted to say. Here I put some references. Here you find the theorem of Gautier, first theorem, which I try to generalize. And then you have sort of about and control theory. So thank you for your attention.
Thank you very much, Michele, and sorry for the technical problem. Right, and technical problems today. If you have any questions, please.
So everything you talked about the second part of the talk was with the acoustic J that was coinciding with the metric induced on the manifold.
Where, sorry?
So when you introduced the
J is the length.
Is the length, no?
In the paper of Gautier, in the work of Gautier, is the length of the Subramanian length of the curve.
And in your
We-
case, it's also
Is the L1 norm of the control?
it's not all the point.
Yes, and which is not really the length of.
Because that's also the
Yes.
measure force you need to stay.
Can it be pushed further with the same techniques? Are there other functions that might be?
Okay, in the case of Gautier is interesting to use the L1 norm of the control because it's the length of the curve, so it's natural to look for the shortest curve. Well, one can think also to other functional. I think I don't know if there are other
I don't
definitions.
know if it's studied, of course it would be reasonable, but and then the basic geometric picture which also your idea is like that. So you have your distance measured by admissible passes. And you have a curve which that is not admissible. So Michele explained very well motivation, motivation, but there is a very clear geometric meaning of the story because the curve actually, if it is not admissible, it somehow present any piece of this curve that is transversal to the class. So the distribution has infinite lengths. So, but still we can measure its complexity, its metric complexity. We take a small neighborhood and measure the length of admissible curve. So any curve can be approximated. It follows also from the curve can be uniformly approximated by admissible. And then when we approximated uniform, so how the length unavoidably goes to infinity, otherwise it would be how fast it goes. We study asymptotics, order of the asymptotics depends. Here the examples, the power was epsilon squared because we need just one bracket here from there. But if you have more, we need more brackets. It's grows faster. It's very easily controlled. Bracket, even in a fine case, it was done by Dario Prandi, I think.
Yes.
The order was computed by
Yes.
but theory of materials, can say developed nice and rather rich theory. Your law computes also principal tolerance. So you grows as 1 over epsilon power depends on structure. But then you compute also a kind of length. So it's some analog of maybe house door measure the kind of length you may compute. And this example, which Michele explained, was this integral part. You clearly, in terms of bracket relation, you simply write this coefficient that is your complexity measured not only structurally but also numerically, how fast it grows, and we can calculate. So that's mainly why the length, because the length is the distance you have to pass. It's infinite, but we can measure. But of course, we can use similar technique with other courses.
Yes, I was thinking, I wanted to understand if there was a specific mathematical reason for which it was important to have in the proofs the length, or if, like, for example, a control from below above of type length given the same thing.
Mathematically similar.
Well, if you have
Probably
constant, if you have
In estimate from below, of course, from above, maybe if there is a different
from
constant.
above,
But yes, for linear system, the length is just your growth. So,
Yeah.
but in a finite, the length has not been measured. He uses exactly what you can take even some power. If that shows,
yes, I think so.
it's a kind of L1, no, but you can take it. Take it even.
Yes, I think that we had P works more or less the same.
It is similar. It's a kind of L1.
I'm curiosity if you can go back to the statement of the theorem.
This one, okay.
Because these three cases can happen. You have example for all the three cases happen.
Well, yes, just you just change the drift, and you have just to choose suitably the drift, and then you are in one of these three cases. So it's just here you can scale A0 with some constant, and if it's small enough or big enough, you have this. You can take yes, a zero constant.
Actually, this drift, the situation changed essentially because it's true that if your linear path is breaker generated, with very big control, you can always eliminate it. You can eliminate controllability from the point of view. It takes simply so big control that even break it somehow eliminates. But here the question is how you should be also numeric play with coefficient. You can now not only try to stay close to the subjective, but also in all application it is present. Just how you do. Even in the pendulum, by the way,
Yeah,
there is a gravitation.
yes,
And it we display it, not only wind, but also gravitation. If you do not apply control, so lift is presented from.
There are no other questions. I think we can thank Michele again and thank you all for coming.